From the first equation we have, if we rearrange the equation, we have that t is equal to x over vxi. Okay, now we have the new expression, the new equation. We substitute this t to the second equation, and we have that y is equal to vyi over vxi x minus half of g x square over vxi square. Okay, so you can see that now we have the relation between y and x, and it has the form of the quadratic equation. This is has the form of the quadratic equation. Okay, and for a quadratic equation, we know that if we plot the curve of y as a function of x, we will have that the path is a parabola. Okay, so we have that the path for the projectile is a parabola, which is shown in this figure. This path, this curve, the name of this curve is a parabola, or this curve, it is a parabola. Okay, now once we know the equation of the path of a projectile, we can next calculate the horizontal length and the maximum height of a projectile. First, look at the horizontal length. The horizontal length is the distance where the object hit the ground. If you look at this figure, you can see that the object starts here, right, and move along the dashed curve, and then when it hit the ground again, the distance from the initial position to the final position in the x direction, we call this the length of the projectile. Okay, it is obvious from this figure that when x is equal to the length of the projectile, we must have that y is equal to 0. Here we consider the projectile on the horizontal ground. Okay, so if we rewrite the equation of the path of the object again, we have that y is equal to the vxi, vyi over vxi x minus half of g x square over vxi square. And if we take y equal to 0 here and solve for x, we will have that 0 is equal to Vyi over Vxi, x minus half of g x squared over Vxi squared. So if we say that when y equal to 0, we will solve for this x, and we will have that x is equal to 0, right? If x equal to 0, on the line of the equation is equal to 0, and x is equal to 2 of Vxi Vyi over g. Okay. Now we have two solutions, but you can see that we have to choose the second solution. It is because if x equal to 0, this is the initial position. Okay, so once we choose the second solution, we have that r is equal to 2Vx I Vyi over g. Okay, so we have the horizontal range of a projectile from this equation. Now let's write down the component of the initial velocity as follows. We have that Vxi is equal to Vi cos theta I, and Vyi is equal to Vi sin theta I. Okay, using this relation, we will have that 2 Vxi times Vyi is equal to 2 Vi sin theta I okay, cos theta I. But from the trigonometric identity, we have that this sin theta I cos theta I is equal to sin to theta I. So we have that the 2 of Vxi Vyi is equal to Vi sin 2 theta I. Okay, so if we substitute this result back to our formula for the range of the projectile, we will have that range is equal to 2 Vxi Vyi over g is equal to Vi sin 2 theta I over g. This result gives us the well-known fact that if we fire a projectile with the same magnitude of initial velocity, what is the angle of the initial velocity that will give the maximum value of the horizontal range? And we know that R max is corresponding to theta I is equal to the 45 degree, and we can show this from this results. This is quite simple because we have that R is equal to Vi sine 2 theta I over G, and our question is that if we fix the magnitude of Vi, this value of Vi is fixed, what is the maximum, what is the angle theta I that gives the maximum horizontal range? This is quite simple, since when R is R max, we must have that this term has maximum value too, but we fix the magnitude of the initial velocity, and G is of course a constant. So we have that at R has a maximum value, the sine of 2 theta I must have the maximum value too. So we have that this is the maximum value of sine theta I. The maximum value of sine function is equal 1. Okay, sine 2 theta I max is equal to 1, and the angle that gives the sine function equal to 1 is 2 pi. So we must have that 2 sigma I is, the sine that the angle that gives the sine equal to 1 is a pi over 2, not 2 pi. So we have that 2 theta I is equal to pi over 2, or we have that theta I is equal to pi over 4, or we write it as a 45 degree. Okay, so this is a well-known result. If we want the maximum horizontal range, the projectile have to fire with the angle 45 degree. This figure shows that result. You can see that all of these projectiles are launched with the same magnitude of the initial velocity. Okay, and when the angle is small, the range is small too. When you increase the angle, the angle of the initial velocity, you have the larger horizontal range, and it is maximum when the theta I is equal to 45 degree. After that, you will have the shorter range and become shorter and shorter, and if you fire the projectile with the angle equal to the pi over 2, it will move back to the original position, and that is the case of the vertical direction.